Hello and welcome back. We've got 3 weeks left in the semester, and we're going to be finishing up our second to last topic today, algorithms and algorithm analysis, and then proceed on to our last topic for the semester, which is going to be trees and tree-based data structures. So today is just going to be kind of a summary of what we've looked at by doing some more examples. And the examples that we're going to be using are, you've seen some of them before. We're going to go back and look at basic searching and sorting algorithms. And then we're going to go through in much more detail on analyzing those algorithms. And I'll give you a few tools along the way. So most of the work today is going to end up being on the overhead here. And we'll start out, I'm going to change the order that I had there a little bit. Let's look at insertion sort, okay? So insertion sort is an algorithm that sorts an array or sorts a collection basically by inserting things. So here's the basic idea. We're going to start at one end, and I'm going to jump right into the middle of the algorithm here. We're going to assume that the first I minus 1 elements are sorted. Okay? And we're going to take the ith element, a sub I, and what we're going to do is we're going to find where it belongs among these first I minus 1 elements, and we're going to insert it by shifting these things down so that we can make room for it, much like an array-based list, and we're going to insert it where it belongs, right? The rest of this stuff, this is unsorted, and we'll go ahead and continue along the next iteration here. We'll then take the next element and insert it where it needs to be, etc. So in other words, we're going to start at A1 is going to be, by definition, it's only one element, so it's going to be sorted. We're going to start at A2, and we're going to determine whether or not it needs to be swapped with A1 or where it needs to be. And then eventually somewhere in the middle of the algorithm, we're going to take the ith element and insert it where it needs to be, maintaining this order over here in the left part of the list. Just to illustrate the idea here, let me go ahead and give you just a random bunch of values here. And let's say that we're going to, there are some other elements in here, but let's say that this is the element that we need to insert. Everything up until this point has been sorted. 2, 3, 7, 15, 17. 1 is out of order though, so what we need to do is we need to insert it where it belongs. And so to do that, we're going to compare it with 17 and see, oh, well, 1 is less than 17, so obviously we need to swap these. All right? Then we're going to compare it to the next element and see, oh, okay, well, yeah, it's less than 17, so we end up swapping them. We end up comparing it to 7, we end up comparing it to 3, we end up comparing it to 1, and all along the way, we end up swapping all of these things. And eventually, we're going to be producing a new section of the list that looks like 1, 2, 3, 7, 15, 17. Right? And we've ended up inserting it where it needs to be. Now, you can look at it as swapping these. You can look at it as shifting these things down to make room for where it belongs and then inserting it where it belongs. Right? Let's look at one more example here. So let's say that the next number is 23, and we need to insert it where it needs to be. Now, we're going to get lucky in this case because we can do one comparison and see that, oh, well, 23 is greater than 17, so we don't need to shift that. We don't need, by making one comparison here, we see that we don't need to swap anything. We don't need to swap anything, and then we can go on with the rest of the list. So I gave you these two extreme examples where one of them we ended up having to shift it all the way down to the end, and the other one we didn't end up having to do any work. This one we had to make 1, 2, 3, 4, 5 comparisons. This one we had to make just one comparison. So remember that when we eventually get into our analysis here, that insertion sort is actually adaptive. That if the list is already sorted, then you end up getting away with less work. Okay? Now what we need to do is we need to take that idea and we need to codify it into pseudocode. Okay? So I'm going to go ahead and start with my standard here. My input is going to be a collection. of elements, A1 through AN, so that I have a name for everything to work with here. And my output is going to be A prime sorted, or A sorted. You can leave it like that. A prime, which is going to be a sorted version of A. Okay. Now let's go back over here to this example really quick. Where do we start? Well, if we start it with the first element here, say that the first element happened to be 2. By definition, an array that is, or a collection in this case, that's empty, or a collection that is only one element, by definition is sorted. So we don't need to start at this first one. We only need to start at the second one, like I mentioned before. So what I'm going to do is I'm going to establish a for loop here. My index is going to start at 2. Remember, we're indexing on 1. It's one based indexing for pseudocode. And I'm going to work up until some value, right? Now, again, if this were the end of our list here, then we would definitely have to go all the way to the end, 23. Even if we don't end up swapping it with anything, we still have to verify that it belongs where it belongs, that it belongs where it is, right? So we do have to go all the way down to the last element, a sub n, okay? Now, instead of swapping these all out, like I did visually here, what I'm going to do is I'm going to take this value and I'm going to put it into a temporary holding, right? The T or something, right? And then what I'm going to do, and instead of swapping this temporary value here, what I'm going to do is I'm going to compare that value to the next thing and see, okay, well, it's my temporary value here is less, so I need to move this over in order to make room for it. All right. So the way that I'm going to do that is by simply capturing that value into a temporary value, a sub I. In general, remember this is the ith iteration, and so we are trying to put the ith value where it belongs. Okay. And I've saved that off into a temporary value. Now I'm going to have to iterate on another value here, j, that I'll start at I. What I did over here is, a sub I here is 1, 2, 3, 4, 5. So this was a sub 6 here. And I'm going to start my index here at this location. And I'm going to compare, excuse me, I'm going to compare this value that I'm looking at with the one right previous to it. So if I'm going to use j as my index value here, I'm going to compare a sub j and a sub j minus 1, the one right next to it. And if this is less than the temporary value here that I'm looking at, then I need to shift this over by copying it. Okay? That's the idea. I'm going to go into a while loop to do that because, like I said before, it's adaptive. With a for loop, you generally use a for loop when you know a priori up front how many iterations you're going to go. If you're going to do it for the entire array, then you have a for loop that for int I equals 0, I is less than this the size strictly less than the size I plus plus, right? Well, this one we don't know exactly how many iterations we're going to go. In some cases, we'll have the worst case scenario where we had to go all the way back down to the beginning. In other cases, the best case scenario, we'll end up only iterating this entire loop once, this inner loop once. And so I'm going to do this with a while loop, okay? And I'm going to leave myself some room here because we're going to have to come back and fill in some additional things. A sub j minus 1, while that is greater than the temporary, oops, sorry, I called it t here, the temporary value t, right? While that's greater than the temporary value, I need to shift them over, okay? And the way that I'm going to shift them over is simply that I'm going to overwrite a sub j to be a sub j minus 1. Okay? And then j minus minus. I'm just going to decrement j. Now, if you don't like that, not all languages support the decrement operator minus minus plus plus and stuff like that. So you can go ahead and go with j is equal to j, or assign the value j minus 1 to j or something like that. It's not that big of a deal. I'll go ahead and use that convention here. Okay? Now, we do have an issue here that comes up when you have the worst case scenario, where you have I and you compare it to the last one, and you finally find out that it belongs at the beginning. We need a different stopping condition there. because I is definitely going to be less than 2, or 2 is going to be greater than I, so we end up shifting 2 over just like we did up here when I was demonstrating this, and then that leaves this open to insert that element there, t. Right? But we need to know we can't go any further. If I went further, then I would be at index 0, and then I'd be off the map here. I would be outside the scope of my array or outside the scope of my collection. So I also need another stopping condition here. While j is strictly greater than 1, and this other condition over here. Okay? Now, if you were actually implementing this in code, of course, it would be while it's strictly greater than 0, right? And it's j here because we're ultimately we're accessing j minus 1, and so we need to stop it at 2, not 1. So that's why I've got strictly greater than here, because 2 compared to the first one, a sub 1, and that gets us our last condition. Then we break out of that loop, and we know that the temporary value here now belongs at location a sub j. So I'm going to place it there. A sub j ends up being, oops, I keep calling it x, and it should be t, right? We're going to take that temporary value and place it at where it belongs, a sub j, okay? There's the idea of insertion sort. And I'm covering this one because it's a little bit different from what you're used to, in that just like a linear search, we're going to have to when we analyze this, we're going to have to be very, very careful because it's adaptive. Sometimes you have the worst case scenario where you make all of these comparisons. Sometimes you have the best case scenario where you only make one comparison. So I'm going to focus, we're going to look at all of those scenarios. But before we do that, let's make sure that we go through our 5-step process. 1, the input is going to be the collection, A. The input size is given to us right here, n elements. 3, the elementary operation. Well, since it's searching and sorting, we're going to, of course, be looking at the comparisons as the most common or most expensive thing here. Again, it's not the only correct answer. You could look at it with respect to the number of swaps or the number of memory accesses or something if you had an engineering problem that you were trying to solve. For us, though, we're going to go ahead and focus on this comparison right here. Now, there are some assignments here. There are, of course, comparisons with respect to this for loop, and, of course, comparisons with respect to this while loop to see if we should jump out of that while loop or not. But those are all necessary for the control structure of the algorithm. We generally do not look at those. Instead, we're looking at the comparisons that actually examine this collection or this array. Okay? Of course, we also have a minus here and a reassignment over there. But this is the one that I want to focus on here. Okay? So for step 4, how many times is the comparison on line, and I didn't number these lines, but 1, 2, 3, 4, 5, 6, and 7. On line 4, execute with respect to the input size here, n. Okay? Now, again, we have a best case scenario where, okay, just answer, well, 1 within that while loop. Or a worst case scenario here where we actually have to make comparisons to everything preceding it. Okay? But before we do that, I'm going to make some observations. On the ith iteration, the while loop executes how many times? Right? So again, in the best case scenario, that inner while loop is only going to execute once. We're going to immediately see that this comparison, this one comparison right here, like with this example, is false, and so we jump out of that while loop immediately. So in the best case scenario, it's going to be 1. Okay? Well, what about the worst case scenario? That's what I really want to focus on, because that's what's going to give me my overall answer here. Okay? Let's look at an example here to understand this a little bit. Remember that this was the sixth element among these, and so I made it 1 comparison, 2 comparisons, 3 comparisons, 4 comparisons, 5 comparisons. Because if we're sorting and trying to find the where the sixth element belongs, well, that implicitly means that there's 5 elements before it. Let's go back all the way to make this a little bit more general, a little bit more abstract. If we're going to sort the ith element, how many elements are before them in order to compare? And if we have to compare all to all of them, we make I minus 1 comparisons. Right? Now, I here is not the I here is the element that we're trying to sort. So in general, on the ith iteration, there are I minus 1 elements to the left. And in the worst case, we have to compare to all of them to shift it all the way down to the beginning. And so my answer here is going to be, thus, at most, I minus 1 comparisons in the ith loop here. Okay? Now, I left myself a little bit of room here because you can look at this from the perspective of an average case comparison. We kind of hinted at this with linear search, that it's going to be, well, the naive way of doing it is you take the best case scenario, the worst case scenario, and then you average them together. I'm going to go ahead and use that same naivete here and look at the average case comparisons as being I minus 1 plus 1, so I divided by 2 or something like that. And I'm going to say that it's about that. So we will come back to this, but this is what I want to focus on for now. Right? Now, when does this happen? When is the best case scenario? That happens when that element is greater than everything, greater than the one right next to it, and so you end up making 1 comparisons and no swaps. So in other words, the best case scenario happens when the array is, or the collection is already sorted. And on the other hand, the worst case scenario here is going to happen when it's sorted, but it's sorted in descending order, 5, 4, 3, 2, 1. If you start here, then that's where it needs to be for now. 4, you end up swapping that. 3, you end up putting that all the way at the beginning. 2, you end up putting that all the way at the beginning. And 1, you end up putting that all the way at the beginning. So the worst case scenario here is when it's in reversed order. Right? And so what does the average case kind of behavior look like? Well, it's when it's, partially sorted. When it's sorted halfway. Right? Or just take any random permutation of elements in the array, and you've basically got this average case here. Okay? So that was my first observation, that on the ith iteration, this while loop here executes a certain number of times. So my second observation is, how many times does the for loop execute on line 1? Right? So I'll go ahead and keep this here handy. So continued. Observation 2. The for loop executes. Now we don't even really have to think about this at all. If we go back all the way to the pseudocode over here, it executes for I being 2, 3, 4, 5, all the way up to n. It executes n minus 1 times. And it executes n minus 1 times because we skipped that first one. Because that it's already sorted. An element of in a collection of size 1 is already sorted. So we skip that first one and start immediately on I equals 2. In other words, I running from 2 up to n minus 2, just as in the pseudocode. So what I want to do now is I want to put these two observations together. Let's look at the best case scenario first. Right? So the best case scenario here is going to be a summation of this is the inner loop. That inner while loop only executes once in the best case scenario. And the outer while loop here executes I being from 2 up to n minus 1, but it doesn't depend. The value here in the summation doesn't depend on anything. We already have our answer up here. That this is, or sorry, this goes up to n. So get rid of that. This is n minus 1 times, right? Which is, now I'm going to skip to part 5 here, or step 5, where you can say that this is linear. Right? So in the best case scenario, you have that that insertion sort. You know, if it gets lucky and it's already sorted, then it's going to be order n. It's going to be linear, right? What about the worst case scenario? Same summation here. I goes from 2 up to n. But remember that this while loop here, in the worst case scenario, is going to be executing I minus 1 times. Okay? Because we have to shift it all the way back down to the end. So I minus 1 here. Now, before I solve this using Gauss's formula, which we've now used 3 or 4, this will be the 3rd time that we've used that. I want to go ahead. You can split this up into the sum of summations by observing that the sum of that the summation of sums, where this is a sum, it's 1 plus negative, or I plus negative 1. You can split that into 2 summations, but I'm going to be even a little bit. There's an even better tool that I can use here. That if I just have I, this is 2 plus 3 plus 4 plus 5. But if I'm subtracting 1 every single time, well, all I have to do is change my indices over here on the summation. If I just take I minus 1, then instead of starting at 2, I can start I at 1. And instead of stopping at n, I can stop at n minus 1. And then I can get rid of that negative 1. I'm pulling that negative 1 into the summation right there. Okay? Now, this looks hopefully very familiar at this point, because this is exactly the summation that we used for selection sort. Right? So selection sort, well, the Gauss's formula would be that it's the summation of natural numbers 1 plus 2 plus 3 plus 4 all the way up to n is going to be n times n plus 1 all over 2. But since we stopped short here, this is going to end up being n times n minus 1 all over 2. Right? And again, skipping to step 5 here, what's the highest order term? It's going to be that order n squared term. Just as a really quick review, let's make sure that we remember how to do that. So let f of n be n times n minus 1 all over 2. We want to show that f of n is order n squared. Okay? All we need to do is set up a summation. F of n, or an inequality, excuse me. We want to show that this is less than or equal to some constant times n squared. Okay? So f of n is n times, and I'll just go ahead and expand it out now immediately, minus n all over 2. Well, we can go ahead and split this up into 2 terms. N squared over 2 minus n over 2. Now remember, input sizes are only ever positive, or at least non-negative. So if I subtract something, I'm making it smaller because this is always going to be positive. I can make this bigger by simply adding n divided by 2, canceling out that second term there. Right? This is less than or equal to, and I'll pull out that 1/2 immediately there, n squared, for all n greater than or equal to 0. It's not true, of course, for any negative n. That's why I'm putting this condition here. But of course, this is algorithm analysis. We don't care about negatively sized inputs because there's no such thing. It doesn't make any sense. Okay? So 1/2 n. So for n not being 0, and c coming directly out of that Gauss's formula for me, c being 1/2, the inequality holds. F of n is less than or equal to c of n squared. Right? Thus, it's going this holds. It's order n squared. Okay? Pretty straightforward. Before we go on, though, I want to look at, just really quickly here, that average case scenario. Remember that we have a summation of I running from 2 up to n, of I divided by 2. Sorry. Well, with a summation, I could just take that 1/2 outside. Or remember, it was -1 or something like that. It doesn't matter. 1/2 summation of I being 2 up to n of I. Right? And we can go ahead and simplify that and come out with basically the same thing. Right? If it was 1 up to n minus 1 or something instead, we're just shifting it down like we did with the last example. Then basically we have just an additional 1/2 out front of what we had before. N times n minus 1 all over 2. In other words, all we're doing is changing this value in front. Now it's 1/4 of n times n minus 1 all over 2. Oh, but then I took the 2 over there. Right? Again, the most the highest order term here is what I'm trying to say is going to be n squared. Right? All that's changing here is that coefficient outside. We're doing, on average, half as many comparisons as before. So again, from the algorithmic perspective, the theoretical algorithmic perspective, there's no difference. It's still a bad order n squared quadratic algorithm. But in practice, if you have a choice between selection sort and insertion sort, you definitely go with insertion sort here, because on average, it's adaptive. And so on average, you have half as many comparisons as selection sort, half as many swaps, maybe you can do that analysis, or ultimately half as much work, period, with insertion sort. In fact, insertion sort is used in practice. We're going to be looking at a couple more sorting algorithms here that are recursive, and like quicksort and merge sort. What generally happens is you're paying for that recursion. And so at some point that the recursion becomes more expensive on small inputs. And what happens is a lot of people will then switch over to an algorithm like insertion sort that is slow in general, but it is faster than quicksort on small sized inputs, say an array of size 20 or 30 or something like that. Right? So it does have its uses. And its use right here is as another good example to apply the things that we've been covering. Okay. All right. So the next thing that I want to cover is something that hopefully you've seen before is binary search. Right. Binary search works by searching for a particular element in a collection that's already sorted. Right. This is why searching and sorting go hand in hand. Because the fast searching using binary search it can only be done if you've already pre-sorted the array or pre-sorted the collection, right? Just to remind ourselves of what this looks like, here's an array that's already sorted, right? A1 through AN. The idea is that you look at the middle element, a sub m, okay? Now the thing that we're searching for a key k. Now, if a sub m is equal to k, then we're done. We found our needle in the haystack, and we can say, oh, we can report that, yeah, we found that element. Otherwise, if k, we're done, is less than a sub m, that means that if that element is in this array, it's got to be in the left half, the left partition. Right? And so we will recurse on the left side. Okay? Otherwise, if the element in the middle here is less than the key that we're searching for, then we know that it's on this side. So we'll search the right side. This suggests that we can write a simple recursive algorithm. Now, usually when I cover this, cover binary search and say CS1, I don't even bother with the recursion. I don't because you can very easily use a while loop and avoid recursion entirely. But for the purposes of this presentation, let's look at what the recursive version of this looks like. Okay. So let me see. I want to make sure that I'm not making any mistakes. So input, output. We'll go ahead. Actually, let's go ahead and do that. Here's my input. Because we're going to have to roll our indices, basically, that we're searching on into the input. But the input is going to be a sorted array. Well, I'll go ahead and call it an array because in general, binary search is not going to work on a linked list, for example, because you don't have random access. If you wanted to jump to the middle element in the array or in a linked list, it would mean that you were doing a linear amount of work to traverse there. Okay, so it's a sorted array, A, and elements A1 through AN. And I will remind you while I'm writing this that we do have the live Q&A session up and running on Piazza if you want to go there and ask a question or call my attention to something that I'm missing. But according to all my feedback, my mic is working. I can read this clearly on my screen. I don't know if you can read it clearly on your screen, but I could get a sharper Sharpie or something like that. Okay? Let me know if there are any issues like that. So my input is going to be an assorted array and bounds L and H, which are indices that are going to be within that array, 1 up to n. This is going to be the left, or the low, and this is going to be the high. So we could call this left and L and R if you wanted to. The left index and the right index. Basically, they're going to start at a sub 1 and a sub n, and eventually I'm going to cut this down in half, cut this in half, cut this in half, cut this in half. Eventually I'm going to be looking at some section of the array, L and H here. And that, I've narrowed it down to this only this one section here. Okay? So that's the point of those. And finally a key that I'm searching for, K. Okay? And my output is going to be A sub, I'll call it just A in A, such that A is equal to the key K. Okay? Now this is going to be the recursive version. Now with recursive algorithms, you have to have a stopping point. Otherwise you have unbounded recursion, and you have eventually a stack overflow on a real computer or just an infinite loop in general. So I need my stopping condition here. Again, what is L and H doing? They are keeping track of the bounds of this array. So I update it until I narrow down onto one element. Okay. What I'm going to do is I'm going to go one additional. So you've got L and R here, or L and H, and I'm moving them towards each other. I'm moving them towards each other. At some point, they could be equal. I still want to make sure that that element that that it's pointing to right there is that the element that I'm looking for or not. But on the next iteration, on the next recursion, they're going to pass each other, and that's going to be my stopping condition. Okay. So if L has exceeded R, or H in this case, then I will output phi. Right? Remember, phi was our placeholder for linear search. That if we didn't find it, then we'll output this special symbol to represent the fact that it was an unsuccessful search. If this were actual programming language, you have many choices. You could throw an exception, no such element exception. You could return null. Or you could return false, or you could also return a negative index value to indicate that it was an unsuccessful search. There are lots of ways that you could implement this. Okay. So the first thing that I'm going to do is I need to find that middle element, and so I'm going to compute the index here, which is just simply going to be the average of those two, and I'll take the floor here because of course you don't have an index that's half. If it's 7 and 2, or 2 and 7, then the average there is going to be 4.5, and that's no such index. So I'm going to take the floor here. This is pseudocode, by the way, and it's perfectly fine to do this. It's not perfectly fine to do this in real life, where this is susceptible to overflow here. All right, if you've got a very large array, and this is say 2 billion, and this is 2 billion and plus 500. Then you've got over 4 billion there, and if you're using an int value for your index, then that's going to overflow before you can take the average of them. Mathematically it works out, but you do have to be cognizant of that actual implementation issue. But there's my middle element. So I simply go through those three conditions that I identified before. If a sub m is equal to the key, then I will output, I will stop the algorithm, I will stop entirely and output a sub m. Right? Else, if the key that I'm searching for is less than a sub m, then I need to search in the left half of the list. I didn't give this a name. I'll call it bin search for short. And so what I'm going to do is I'm going to make a recursive call here. Bin search, binary search, and I'm going to have to pass it all a bunch of inputs. Well, A is unchanged. My key is unchanged as well. But now this corresponds to searching the left half of the list. The left half of the list here is going to be whatever A sub L was before, and here's A sub M. It's not the thing that I'm looking for, so I'm going to have to go one less than it, A sub N minus 1. I don't include A sub M. Some implementations do, but I'm not going to include A sub M simply because we already checked for it. Right? If that's why should I continue to keep that in my search if I know that that's not the thing that I'm looking for, because I've ruled that out from these two lines right here. So I'm going to go with L and M minus 1 as my low and my high. And of course, key K is unchanged here. Else, now this can be a regular else statement, but I'm going to explicitly say that else if A sub M is less than the key, then you need to search on the right half of the list. And again, this is not necessary in general because it's either equal, it's strictly less, or it's strictly greater, or in this case I switched them around. But it's not necessary to do this comparison, but I'm driving home the point of what we're looking for here, or what we're doing with this algorithm. Now in this case, I update the left index here to be on the other side of M, and my right index, or my high index here, is unchanged. And I make recursive calls there. Okay? Now we're going to have to analyze this. Now, if this were the iterative version, I could very easily set up a summation and show that it goes all the way down to until I is the size of the list. The size of the list is initially n. Then we cut it in half, cut it in half, cut it in half until we get down to a list of size 1. But that is not going to work in this case. I mean, it's the same basic idea, but it's a little bit different here because it's a recursive algorithm. So we're going to need a little bit more, a different tool here. Step 1, Step 2, and Step 3 are the same. The input is, of course, the collection A. Step 2, the size of the input is initially it's n in general, but for any one recursive call here, it's going to be the size, however many elements are between L and H. So it's going to be something like H minus 1 divided by 2, all right, whatever, right? Well, let's just go ahead and keep it n for easy analysis for this one, okay? And the 3, the elementary operation. Well, there are several comparisons here. For example, there's a comparison to see if it's equal. There's a comparison to see if it's strictly less than, and there's a comparison to see if it's strictly greater than. Well, as I said before, this one is not necessary because it's either one of these 3. So we can eliminate that immediately. So we're not making 3 comparisons, we're just making 2 comparisons. Now I'm going to simplify this even further and say that these are actually the same comparisons. Think about what you do in practice. In practice, you would actually do a comparator function or a comparator object, and you would pass it these 2 elements, and it would do some complex business logic, do a bunch of string comparisons, value comparisons, or whatever. At the end of the day, it's returning something negative, something positive, or 0, depending on the relative ordering of these 2 things that you're giving the comparator. Okay, that's really only one comparator call. The rest of the stuff, to see if it's positive or negative, positive, or 0, that's necessary to the control structure of the algorithm. So I'm going to get away with saying that there is one comparison on each call to this recursive function. Right? So let's put those observations together. One observation is that each recursive call only makes one comparison. Right? The input size to each call is n. Now n is going to be changing. Initially, it's all n elements, and then it's n divided by 2, n divided by 4, n divided by 8, etc. Right? But what I'm going to do is I'm going to say that I don't care what came before. I only care about what I'm doing right now. That there is I'm looking at a subarray of size n. N is going to change, yeah. But for the purposes of this recursion, I'm going to assume that, well, the input is always of size n. Initially, it's n, then it's n divided by 2, n divided by 4, etc. But I'm just going to give it the same name for the purposes of figuring this out mathematically. Right? My last observation is that at most one recursive call is made. Remember that in the pseudocode, these three conditions are all mutually exclusive. That it's either equal, it's strictly less than, or it's greater than. Right? These observations are enough to set up what's called a recurrence relation. Right? So let C sub n be the number of recursive calls by binary search, by bin search, on an array, collection, whatever you want to call it, of size n. That's why I didn't want to mess with the decrementing of n here. I'm just going to keep it simple, C sub n. Okay? What we need to do is we need to express C sub n as a recurrence relation. That when I call it initially the first time, I make one comparison and then I recurse on an array of size n divided by 2. Right? Well, I can expand that out and I make one comparison and then I recurse on an array of size n divided by 4. Right? I can expand that one out and I have one comparison plus and then I make a recursive call here of n divided by 8. Right? Dot dot dot. Until you get down to an array of size 0, in which case I make 0 comparisons, and that's when the recursion stops. Right? That's the idea there. To do this, though, I don't need to. I'm basically what I'm doing here is I'm unrolling the recursion, and that's what I would do if this were an iterative version, an iterative presentation. But I'm not going to do that. What I'm going to do is I'm simply going to set up a single recurrence, and then we're going to bring in another tool here. So C sub n makes one recursive call on an array of half the size, roughly half the size. Now, again, it's plus, minus 1, minus 2, whatever. There's something called the smoothness rule that allows you to ignore those things, right? So there's one recursive call on an array of size n divided by 2. Why did I write it C sub n divided by 2? Because remember, what is C capturing? It's the number of recursive calls by binary search on an array of size n. Well, we've got an expression to take care of that, right? This is the recursive call. That's not a number, that's another expression. Right? And then there's one, this is the non-recursive comparison. Right? I'm leaving it like that. Again, what I was doing was I can unroll this and I can solve this, and all I need to do is determine what is the depth of this recursion, and then there is 1 plus 1 plus 1 dot 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 plus 1. The depth tells me how many ones I added up here, and of course you'll get the usual answer of it's going to be something logarithmic. I don't want to do that. I want to pull in another tool here that is of more general use, and we'll come back to this here. It's called the Master Theorem. And unfortunately, it's kind of a misnomer because it's actually only useful in very, very niche situations. Searching and sorting algorithms come up all the time with this. But basically, it says that let T sub n be a recurrence of the form T sub n is A times T sub n divided by B plus some f of n, right? Where f of n is going to be some usually bounded by a polynomial function. Order n to the k. Right? Okay. Then, what the master theorem tells us is we don't have to unroll this. We don't have to solve it. All we need to do is identify a, b, and k, and that gives us a quantification, a big O characterization of T sub n. There are only three cases here. It's going to be order n to the k if a is less than b, strictly less than b to the k. It's going to be order n to the k log n if a is equal to b to the k. And it's going to be order n to the log base b of a if a is greater than b to the k. Okay? And we'll come back to this here after I've explained this a little bit more. So, if we have a recurrence of this form, where you are making a recursive calls, the recurrence is more general than this, but in the context of algorithms, you are making a certain number of recursive calls. You are cutting the input size by some constant. If b is 2, then you're cutting it in half. If b is 3, then you're cutting it into a third, right? So you're only looking at that. There is something called ternary search, where you divide it up into 3 sections, and then you determine which section it's in. It doesn't really buy you much. And then you're doing some non-recursive cost here. So you're doing a number of recursions. Those recursions are cutting the input size by a constant factor. And you're doing some non-recursive work that can be captured by a polynomial. What this case is saying is basically you're making fewer number of recursive calls than you are doing non-recursive work. This one is saying that you are making more recursive calls than you're doing non-recursive work. This one is saying that they're kind of equal, that you're doing just as much work in your recursion as you are in your in the non-recursion, right? To set up the recursion, basically. Okay. What about binary search? Binary search. What are our coefficients here? A is equal to 1. B, we're cutting it in half each time, so B is equal to 2. And what is K here? Right? Well, this is a constant. Yes, it's true that this is order n. In other words, K being 1. But that's not tight. Right? That a constant is going to be order 1. This is true, but this is more true. Right? This is going to be more helpful here. Well, what's my K then? Hopefully you see that this is a degree 0 polynomial. So my K is going to end up being 0. Okay? It's just plug and chug at that point. All you have to do is set up a recursion. That's the real magic. That's where all the work is. Once you've set up a recursion, and that recursion conforms to this this form, then all you need to do is identify A, B, and K, and plug and chug. So what is the relation between A and B to the K? Well, A is 1, and B to the K, well, that's going to be 1. So these two things are equal. If they're equal, then by case 2 of the master theorem, case 2 applies. And that we've got C sub n is going to be order n to the k log n by the master theorem. But remember, what is k? 0. So that term actually disappears. And we've got that this is order log n. An extremely efficient searching algorithm. Of course, it needs to be sorted before you can do that, and of course, it needs random access. But it's an extremely efficient searching algorithm, right? Provided, of course, those two other conditions apply, right? And hopefully, you've seen this before with respect to the iterative version, just using a while loop to cut it down in half each time. That usually involves not setting up a recursion, but basically doing this math manually without any recursion and with no use of the master theorem. But I like to cover the master theorem here because it's going to apply in the final two examples that we've got. Right? What I'm going to do is I'm going to present one of them, but I'm not going to present the details of the code. Instead, I'll save that as an exercise. And then the other one, I will present again that you might have seen the idea at least, and we will go through as much as we can as far as the details go, but otherwise I've got another video on it if you want to take a look at it. All right, and I'll post that at the end. So the first one that I want to show you is merge sort. Now the idea behind merge sort is that you have two phases. One, you have a divide phase. And this is usually comes up with recursive algorithms. It's a divide and conquer kind of thing. You divide. You split the array into two parts. Right? So if there's an array, we're simply just going to cut it in the middle, and here's the left part, left partition. Here's the right partition. Okay? And you conquer. The way that you conquer is you keep doing this, keep dividing until sorted. Right. Now, it's not that simple as far as the whole thing goes, but that's the idea. You just keep dividing it until it's sorted. What's something that's sorted without having to do any work? In other words, you keep dividing until sorted. You keep dividing until the size is 0 or 1. Right? By definition, that's sorted. If it's an empty array, then by definition it's sorted. It's vacuously true that it's sorted. And if there's only one element in there, then there's nothing else to compare it to, so by definition it's sorted. Only when you have two elements or more do you have to actually worry about the ordering. Right? So that's the conquer part. There's a combine part at the end. So given two sorted arrays, that this one is sorted, A is sorted, and B is sorted, then all we need to do is we merge them together. And the way that we do that is what I'm going to concentrate on as far as this algorithm goes, because hopefully this is pretty straightforward. The recursion will simply be almost exactly what we had for binary search. That we start at we start at 1 and n, we find the middle element, and then we put that off into a recursive call, we put the right one off into a recursive call, and the very last step is simply going to be, oh, well, if it's 0, then it's already sorted, so we'll go ahead and return that empty array. If it's 1, okay, well, it's already sorted, we'll return that empty array, okay? So basically, if you want to look at it visually, if you've got 3, 7, 1, 2, 8, 4, 0, 5, right? Then you divide it, right? And we won't worry about this other half here. You divide that. You divide into 3 and 7. Then furthermore, you divide that into 3 and 7 and 1 and 2. You divide that further into 3 and 7 by itself, and 1 and 2 by themselves. And then you start merging them together. You combine these, you combine these, you combine those back, and then this would have gone their own route here, and so ultimately you combine that back as well. That combine is what I want to focus on here. Okay? So what I'm going to do is I'm going to fast forward through this algorithm right here, and I've got 1, 2, 3, and 7. That's the left partition sorted there. The right partition sorted is going to be 0, 4, 5, and 8. Now, how might you merge these together? Suppose that these are my two arrays right here. What we're going to do is we're going to establish another array. Right? That is going to be our combine. We're going to merge them together into this array. All I need to do is keep track of two indices, index I and index j. Okay? And what I'm going to do is I'm going to compare the one in the left, L sub I, right? And I'm going to compare the one in the right, R sub j. And whichever one is less, I'm going to copy it down over here. And then I'm going to increment my j to be the next one. If I copied the thing on the left-hand side, like I would in the second iteration here, then I copy that over and I increment I. Right? Now I and j are pointing here. I continue. 2 is less than 4, so that gets copied over. And I is incremented. 3 is less than 4, so that gets copied over before we move on in J. And at this point is 7, okay. Now 4 gets copied, merged. And J is incremented. 5 is still less than 7, so 5 gets copied. And now I'm looking at 7 and 8. Well, 7, that gets copied next. And at this point, this index has fallen off of its left partition. And at that point, what I can do is I can play fast forward and say, all right, well, whatever else might remain here, go ahead and just copy it over. There's only one element in this case, but if there are 50 elements, then I wouldn't have to make any more comparisons. All I'd have to do is copy over those 50 elements. One of these is going to get to the end first, meaning that I switch over into a pure copy mode, copy everything in the right-hand side, or copy everything in the left-hand side, and I end up getting merged. Right? My observation on this here is that for each copy, one comparison is made. That's why I'm not going over the pseudocode. The pseudocode is available in the Computer Science 1 book and a couple of other locations. But for each copy, one comparison is made. There are n elements over here, n elements over here. Let's just go ahead and combine those and say that there are m elements over here and there are m elements over here, and altogether n is equal to 2m. Right? In other words, to merge two arrays, each of size m, which is n divided by 2, into one of size n, requires that you look at every single element over here. Now, you might get lucky, and after making n divided by 2 comparisons over here, you ended up copying everything over here, and you don't have to do any more. But ultimately, you're going to be doing about n comparisons in the worst case. Right? This is the non-recursive part. This over here, the divide part, that was the recursive part. Right? So what I'm going to do is I'm going to combine those two things and come up with a recurrence here. And then we're going to go back to the Master Theorem and use that as a tool now. So what I'm going to do is C sub n is equal to the number of comparisons of merge sort on an array of size n. Okay? And all we have to do is set up our recursion here. Remember that we're taking an array of size n and splitting it up into two arrays of size n divided by 2. We're recursing on that, and then when we return from the recursion, we're doing a certain amount of non-recursive work in order to merge them back together. Okay? So we are making two recursive calls, one on the left-hand side, one on the right-hand side, to arrays of size roughly 1/2. Now again, the smoothness here, if you have 9 elements, one of them is going to get 5 and the other one's going to get 4. So it's not exact, but it's roughly, right? And that's good enough for the Master Theorem. Right? Plus, we're going to be doing this merge operation when we come back from it. Remember that merge operation, if we divided it into one that's of size n divided by 2, and one that's of size n by 2, and combine it into one of size n, we end up doing n comparisons. Actually, n minus 1, because we'll get away with at least one comparison. But I'll go ahead and leave it like this, right? So, again, this is two recursive calls. One for each list. This is my input size here. Size is about 1/2 for each. Right? And then this is my merge operation. Merge the two after recursion. So that's the recursive setup that I now need to solve You can solve this by unrolling the recursion and doing some mathematics and stuff like that. But again, who cares about solving this when you've got a tool like the Master Theorem? So all we need to do is identify A, B, and C. A is 2, B is 2. Remember, 2 recursive calls, each on half as big. And then, in this case, K is going to be 1 because this is order n to the first. Okay? What is the relationship between A versus B to the K? 2 versus B to the K here is 2 to the 1. Again, they're equal. Right? And this is why I said that the Master Theorem is kind of a misnomer, because with a name like Master, you can kind of get the feeling that it can take care of a lot of cases. All the cases that come up with algorithm analysis generally tend to be case 2, unfortunately. Right? So by case 2 of the Master Theorem, we have that this is going to be order n to the k, which is just 1, log n. And that's our quasi-linear function that we looked at the very beginning. Order n squared is not acceptable for even for today's data, but order n log n is very acceptable. So unlike selection sort and insertion sort, which are slow algorithms because they both have a worst case scenario, worst case running time of order n squared, this one at least gets us down to n log n. Of course, the best that you can ever hope to do, you have to look at the entire input, unless you've got some probabilistic thing going on, or you have some additional assumptions about your input. The best that you can hope to do is order n, because you have to look at all of it. By having this additional logarithm over here, it's almost linear, right? The best you can do is linear. This is quasi-linear. That's really, 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 really close. And in fact, there is a mathematical proof that shows that any index or any comparison-based sorting algorithm has a lower bound of n log n. So merge sort is basically as good as you're going to get for general sorting algorithms for as far as asymptotic analysis goes. Okay. All right. Well, we have about 10-15 minutes left. You know what? I'm just going to go ahead and call it early on this one. And what I'm going to do is I'm going to post the link to it, because a year ago I did quicksort. Quicksort is we do quicksort generally in Computer Science 1. The idea, let me just give you the idea to refresh your memory. Quicksort is an algorithm that chooses a pivot element over here, right? Without loss of generality, just suppose that we grab the first one. And then it goes through the rest, and anything that's less than this pivot element, it's going to put over here. Everything over here is going to be less than the pivot element P. Everything, but if it's greater than the pivot element, what it's going to do is it's going to take each one of those elements and going to throw it over here, and everything over here is going to be greater than P. So if you've got everything that's less than P over here and greater than P over here, where does this pivot element belong? Right in the middle. P ends up being sorted and you're done. All right? Don't move P. Then what you do is you recurse on the left side, you recurse on the right side, and you continue that process down until you have an array of size 0 or 1, very similar to merge sort. And I'm not going to go through the whole process here, because I generally cover this in Computer Science 1. I've got a video from a Lightboard session that I did that I'll post instead, and you can watch that at your convenience, where I actually go through the code for doing this. The code is also available in the Computer Science 1 textbook. But basically, one thing that I don't do is I don't do the analysis for this. I do it in the other video, but you can kind of already see that in the best case, you're going to end up with 2 subarrays here, roughly of equal size. So you're going to have to make 2 recursive calls on an array that's about half as big. Right? Now, what about the non-recursive cost? Once we chose our pivot element, we had to look at all of these elements and say, oh, it belongs over here, or it belongs over here. We had to make a certain number of comparisons. We had to make n-1 comparisons. n-1 because if there are n elements here, we don't compare the pivot to itself. We compare the pivot to everything else and say that it belongs over here or it belongs over here, and then we just simply insert the pivot at the end. Well, that looks really, really familiar at this point. A is 2, B is 2, and K is going to end up being, this is order n, so K ends up being 1. 2 is equal to 2 to the first, and so by case 2 of the master theorem, the best case running time of quicksort is going to end up being order n to the k, which is 1 log n. Right? So it's essentially going to be the same thing as merge sort in the best case. Now there is a worst case here. The worst case would be when you choose your pivot element here, p, and everything else belongs on one side. And you end up, and then the right side here is empty. Right? And you end up putting p at the end, or you end up leaving it at the beginning. In other words, it was already sorted, and your choice of pivot element here means that everything stayed on one side, or you shifted everything over to the other side, making a linear amount of work even though it was already sorted, or in this case it was already sorted in reverse order, in which case you don't have this recurrence. In the worst case scenario, you end up doing one recursive call because you don't need to make a recursive call on an element of, on a list of size 0. So you make one recursive call, and you don't end up cutting it in half either. You end up cutting it of size 0, and over here it's going to be n minus 1. But you still do that linear amount of work there in order to put everything to one side or the other side. Now, this is where the master theorem fails us. And again, this is why I say that it's a misnomer. It's misnamed because it's not really the master of anything. The worst case scenario here does not apply because it's not in that form. It's not in the proper form to apply this. Instead, what you have to do is you have to solve this. This is a linear, non-homogeneous recurrence relation of degree 1 in this case. Solving that stuff is 235 material. That's a discrete mathematics. You'd have to come up with a characteristic equation of degree 1. You'd have to solve the non-recursive version, or you'd have to, this is actually pretty easy, you can just unroll the recursion, but it ends up being, spoiler alert, it ends up being order n squared. So in the worst case, quicksort does devolve into basically what's a selection sort, because if it's already sorted, you select the minimum, and then you end up comparing it to everything and seeing, oh, it's where it needs to be. I don't move it. You select the second minimum, third minimum, fourth minimum, making a linear number of comparisons each and every single time, and ending up not doing any actual swapping. Right? So if it's already sorted, sorted but in reversed order, then it kind of devolves into the selection sort here. Okay. Again, I'll post that video for full details. Otherwise, the full pseudocode is available in the Computer Science 1 textbook. That basically concludes algorithms and algorithm analysis for this course. What we'll be doing for the next 2.5 weeks now, when we come back on Thursday, are trees and tree-based data structures. We'll go through the basic definitions for trees, which are basically acyclic graphs. We'll start to orient them so that they are binary trees, so that we're going to iteratively give them more and more structure, because what is this course about? It's about data structures and algorithms. And we want structure in our data structures because we want structure to exploit. If we can exploit that structure, like we did with binary search, we exploited the fact that it was sorted. We exploited that fact to get away with an exponential speed up in over, say, linear search with binary search. And we're going to continue giving data structures more and more structure that we can exploit to make things more efficient. So we're going to be looking at that. We're going to be looking at binary search trees. That's that's how we can give them even more structure so that they actually hold things. A structure is useless unless you're actually holding data within it. And then we're also going to look at a related notion called heaps at the very end. And then we're going to bring it all the way back to searching and sorting and apply those data structures to a new sorting algorithm. Okay, and that's the remainder of the course. So again, if you joined us live, thank you. Otherwise, go ahead and post on Piazza with any further questions. Have a good day.